Good afternoon, everybody. Welcome to my talk. I will briefly talk about what is a choke species and why it may be a problem under the landings obligation, and how RTI may offer a solution to this problem. The big question is, of course, how can RTI do that? And the answer is by complex algorithms behind the scenes while being simple in use. I will spend some time explaining the algorithms for RTI that I explored. Be warned, it is complex and I cannot make it easier. So first briefly, what is a choke species? In a hypothetical mixed fishery, the choke species is the species whose quota is exhausted first. Under landings quotas, where fishers are allowed to continue fishing until they have taken up all of their quotas, this means that they will overcatch species A and C, which they are not allowed to land and thus have to discard. Managers often set effort restrictions to limit the effort to that needed to catch species A. This species then chokes the fishery because the quotas for species B and C cannot be fully taken up. Similarly, in the case of catch quotas and the landing obligation, at least under the worst case assumption that the three species are caught unavoidably together. Fortunately, the worst case almost never exists, and catch compositions vary at a fine spatio-temporal scale. This makes it possible for fishers to target and avoid species, and thereby approach the catch limits of the three species more precisely. And indeed, the paper by Branch and Hilborn describes that in British Columbia, fishers are able to fish up their quotas rather precisely by targeting and avoiding. But the price they have to pay is that they have to keep track of up to 22 different quotas. In RTI, fishers will have to keep track of only one quota. RTI is a new management approach that Dave Reed and myself have proposed a number of years ago. At every ICES annual science conference since 2011, I have been talking about it. Basically, each fisher gets an individual allocation of fishing impact credits, we call them RTIs, for example 200 per year. With those, fisher can fish when and where he wants, as long as he pays according to spatio-temporally varying tariffs that are displayed on maps such as this one. The managers will set the tariffs according to their objectives. They may close some cells, such as the black ones here, where they want to prohibit fishing temporarily. But otherwise, they will set high tariffs, for example, of 5 RTIs per day in the red regions, where they want to discourage fishing, for example because in those regions the catchability is high of the species of which the fishing mortality needs to be limited. In other areas, the tariffs can be quite low, such as 0.1 or 0.5 in the white and yellow areas respectively. In those areas, fishing is encouraged, for example, because the catchability of the vulnerable species is low there. I will now explain the algorithms I propose to set the tariffs for multiple species simultaneously. Other algorithms are possible as well, but these are the ones that I explored in a simple simulation model. I ask you to bear with me. It is not really difficult. It's just that it's rather difficult for a talk, but I have to do it because in none of my earlier talks on RTI have I actually explained how it works. So take a deep breath. Okay, so there is the initial tariff setting. There is the within-year tariff updating based on real-time CPUE information, for example at a weekly timescale. Other timescales are possible as well. And there is the between years annual adaptation based on a harvest control rule that calls for action as soon as the realized estimated harvest rate deviates by more than 10% from the target. Let us for the moment skip the initial tariff setting. So let me now first explain how the short-term, let's say weekly, updates work. The procedure has steps, species by species, and then to combine them. Okay, so there are 6 tariff colors: white, yellow, light orange, dark orange, red, and black. Now imagine that of the grid cells of a map of the management area, for each species, so we start with species 1, per grid cell, the CPUE of last week is calculated and expressed relative to the mean of that week. They are then assigned to color-coded CPUE classes. So, for example, if the CPUE is less than 10% of the average, it is white. And if it's between the average and twice the average, it's dark orange. Now the rule is that if the CPUE class color of last week is higher than the tariff color of last week, then the tariff will go up by 1 color. You see, if the tariff was light orange and the CPUE class red, the new tariff will be dark orange. We never change by more than 1 level to avoid large fluctuations. Similarly, if the CPUE class color of last week is lower than the tariff color of last week, then the tariff will go down by 1 color. So if the tariff was light orange and the CPUE class yellow, next week's tariff will be yellow. Okay, then we repeat this for each species, first for species A, then for species B, and then for species C, to arrive at the new species-specific tariffs. Now these need to be combined in the tariff to be set for that week. We simply do that by taking the highest of the 3, which is precautionary. So for each cell, each week, a tariff will be set that is the highest of those that would be set for the individual species. Okay, now we come to the annual harvest control rule. Just as in usual management, there will be an annual assessment that finds out whether last year the harvest rate was close to the target or not. In my algorithm, if it deviates more than 10% from the target, above or below, action needs to be taken. Namely, that the tariffs need to be more stringent if the harvest rate was too high, or less stringent if the harvest rate was too low. So, while the weekly updates change the cell tariffs only relative to each other, the annual adaptations will make the overall level of tariffs more or less restrictive. So here you see for each of the 3 species the boundaries between the CPUE classes that give rise to the tariffs as just explained. Now imagine that these boundaries can be multiplied by a multiplier. In the default case, this multiplier is 1. Now imagine that for species A, the harvest rate was too low and deviated from the target by more than 10%. According to my harvest control rule, the tariffs should become less restrictive. My rule says increase the multiplier by 10%. So it becomes 1.1. And all the boundaries here get multiplied by 1.1. Now imagine that the harvest rate was too high. The tariffs must be more restrictive. My rule says decrease the multiplier by 10% and it becomes 0.9. And all the boundaries become multiplied by 0.9. So you have to realize that the effect is that now, already with slightly lower CPUEs, the tariffs will be higher. Because we knew in advance that species A is the choke species, and species B needs the most effort to achieve the target harvest rate, and species C is in between, we can already start out setting the multipliers at different values. So for species A, cells with just above average CPUE get a dark orange tariff, whereas cells that have just above average CPUE of species B get only light orange tariffs. Those are the species-specific tariffs. You still have to realize that in the week-by-week tariff setting, for each cell, the highest of the three will be set as the actual tariff. Now, over the years, when you apply this harvest control rule to each species, the multipliers can quite diverge, as you can see here. Species A, the choke species, got quite a restrictive multiplier, while species B has a very mild one. So now we can have the situation, look at the row with the yellow tariff, that cells with above average CPUE for species B, but low CPUE for species A, can have a yellow tariff, which is relatively low, namely only half an RTI per day. So there will be regions where species A can be avoided and species B can be targeted at relatively low expenditure of RTI credits. So these are the algorithms I explored. And these are being implemented by OLRAC, the e-log company of Amos Barkai, into the onboard and onshore software to make the system operational. Now I am at the end of my talk, but I haven't told you about the simulation studies yet. I gave a talk on these at a conference in Rome last March, and I uploaded it on YouTube. The link to that video is in my extended abstract, so you can find out more about my simulations there. But just briefly, the model is an abstract model. We call it a toy model. In it, 100 fishers are distributed equally over 3 métiers, each métier targeting one of the 3 species, while the species spatial distributions vary independently of each other. While conventional TAC management leads to 100% and 33% overfishing respectively, and effort management to 50 and 33% underfishing respectively, RTI will typically approximate the actual targets quite closely, and in this particular case you will have only 4% overexploitation and only 12 and 6% underexploitation respectively. Thank you very much for your attention.